Welcome back, everyone. So the next talk is by Weiwei Cui from Lund University, who is going to talk on Hausdorff dimension of escaping sets for Speiser functions with few singular values. Thank you.
Hi, thank you. So can you hear me clearly? Okay. So, yes. So it's a pleasure to give a talk here in a conference. And today I'm going to talk about some work with joint work with Magnus Aspenberg from Lund University. It's about Hausdorff dimension of escaping sets for the functions in a Speiser class, as with relatively few singular values. So I will first talk about some Speiser functions, but in this case, I'm talking about meromorphic Speiser functions, and also some Hausdorff dimension of escaping sets for the functions in the Speiser class or in the Lund class. And also the main point is the construction of function with the Speiser function with some given Hausdorff dimension with escaping set. So first, I recall you some definitions of singular values, which you might know already. We have a meromorphic function in the plane, and we say value is a singular value if it is either critic value or asymptotic value. So critic value means that it has a pre-image with vanishing spherical derivative. It means that function is not locally injective at this point. So then it is a asymptotic value if you have curve going to infinity and the image of curve approaches some value which can be finite, which can be infinity. And well, we already know many examples of transcendental functions, like for the exponential function, you have this asymptotic values at 0 and infinity. And for some meromorphic function like tangent function, you have two asymptotic values, but no critic values. So it's locally invariant function. And for the same function, which is the entire function, you have two critic values, which are at plus and -1. And at the same time, infinity is always a asymptotic value. And this is also true for every entire function. So with the definition of singular values, then I recall you the definition of Speiser class, which means that it has the function has only finite many single values. So here it could happen that infinity. Here I include infinity in the definition of single values. So it could be that infinity is a single value. But it also happens that infinity is not single value. For example, here, if you have tangent function, then infinity is not a singular value. But on the other hand, you have entire function like exponential function and sine function, then they both have infinity as singular value. Also, there are some other examples like where starts P function. It also belongs to the class S. It has some critic values, but no asymptotic values. I will talk about these functions later. So compared to the Speiser class, a large set is the so-called Lund class, which is a set of functions with a bounded set of finite singular values. So here we only count the finite singular values because, as I said before, infinity for the meromorphic function can be a critic value or asymptotic value. So we call these functions Lund functions. So I will also recall you the definition of order or growth of function in the meromorphic setting, which is defined by the nonlinear characteristic function. If the function across the function is the entire function, you can replace the t function here by the modulus function, log of the modulus function. So roughly, let me recall you here, maybe. I mean, if you have entire function, you have entire function, you can replace here by log MRF. and MRF is the maximum modulus. So, but for in general, for meromorphic functions, let me clean this. In general, for meromorphic functions, if infinity is not an asymptotic value, then it must have infinite manifolds. So this is the result of Iverson. On the other hand, if infinity is not a asymptotic value, but the function belongs in class B with some additional assumption on the multiplicity of poles. For example, the multiplicity of poles are, if they are bounded, then actually you can compute the autogrowth of the function by the counting function of the poles. So here we have the rho of f with the order function is actually, you can replace this TRF by the counting function in RF here. What Teichmüller's result says is actually if function in class V infinite not asymptotic value and you have bounded multiplicity of poles, then the characteristic function is almost equal to the iterated counting function, but the iterated counting function has the same growth scale of this counting function. So you can get this. And for Speiser class function, because it has finite single values, I will denote function denoted by SQ, the function Speiser function with exactly Q single values. So we have many examples like exponential map belongs to S2 because it has single values 0 and infinity, and sign map it has 3 because there are 2 curve values plus minus 1 and also infinity as a asymptotic value. On the other hand, for the P function, it belongs to S4 because it has 4 curve values and no asymptotic values. I will also recall you that two functions are equivalent if they are two functions. Here I only restrict myself to Speiser functions. So we see two such functions are equivalent if there exists two homomorphisms of the plane such that this relation holds. Homomorphism here can be replaced by quadratic conformal homomorphism. So roughly it means that two functions are equivalent. This means they stay in the same prime space. And the class of this equivalence class is, the set of equivalence classes forms a dimensional manifold. So, but I'm not going to talk about this. So, first we discuss functions in S2, which roughly means that function with, it means that function has two singular values. But in fact, if a function has only two singular values, it has a special formula. It has very explicit formula you can write down explicitly. So such function can be represented as a composition of exponential map with a affine map and Mobius transformation. So you can prove this by covering space argument. But here the consequence of this fact is means that it means a lot of properties of the function in this class. Like the function, the order function is always 1 for any function in this class, and function is periodic. It has only two singular values, which are actually omitted values, and essentially there are only two equivalence classes. One of them is exponential map. It's because if you have two single values, if one of them is at infinity, one of them is in a finite plane, then you have exponential family. But if both two single values are in a finite plane, then you have tangent family. They are equivalent to tangent family. But what happens if the single values are bigger than 2? So a natural question is how many equivalence classes for SQ if Q bigger equal than 3. But the answer is quite clear. There are uncommon many such classes. You can see this for entire functions. Roughly, you are looking for entire function with two finite single values. For this, you can resort to the query conform folding technique or based off, or you can just consider some infinite planar tree in the plane satisfy some uniform condition on the topological condition on the trees. Then you can each such infinite tree will correspond to an entire function with two correct values, but you have uncounted many such trees, so you have uncounted many equivalent classes. For the meromorphic functions, you can meromorphic function means here means it really have poles. You can look for meromorphic function as well with rational surrounding derivatives. This is a very old work of Elfring. But in general, you can get such functions by using the theory of Speiser graph. It's also very old theory. The main topic is about Hausdorff the escaping set, but I guess escaping set is quite clear. The definition is quite clear to both of you. So all of you. So escaping set is just a set of points which escape to infinity and iteration. So this set is non-empty. It was proved by Ermanco for entire functions and by Dominguez for general meromorphic functions. But if the function belongs to a class B, then you have stronger results that escaping set is a subset of Julia set. Well, actually, Julia set is the closure of the escaping set. So these are results by Ermanco and Lubitsch for entire functions and by Rippey and Stellers for meromorphic functions, for transiting meromorphic functions. So with this result, I want to talk about Hausdorff the dimension of escaping set, but before that, I want to mention two results which address the role of infinity in estimating the Hausdorff dimension of escaping set. First, if you have a function class B, meromorphic but of finite order, but if infinity is asymptotic value, then Hausdorff dimension of escaping set is 4, it's 2. So on the other hand, if infinity is not asymptotic value, it could happen that the Hausdorff dimension of escaping is not 2 anymore. So in further results by Weiwei, Kempinski, and Stellers, they show that infinite asymptotic value you have 4 dimensions, but in the entire function case, it was due to Bronsky and the Schubert independently. So and in the second result by Becquerel and Coulters, they put some, if infinity is not asymptotic, they put some restriction on multiplicities of poles. They say that if the multiplicity of poles are bounded, then the Hausdorff dimension is strictly less than 2. Well, there's a very explicit upper bound estimate for the Hausdorff dimension in terms of the order growth and also the multiplicity of poles. But I think the underlying reading for these 2 different results is if infinity is asymptotic value, roughly the function, the point escape to infinity will by staying in the tract, logarithmic tract. On the other hand, if the infinity is not asymptotic value, and if the point escapes to infinity by jumping between poles and poles, so the multiplicity of poles really plays a role here. Also, if the poles, multiplicity of poles is are not bounded, then you can have 4-dimensional escaping set. You can even have escaping set of positive Lebesgue measure. So I would also like to address the difference of Hausdorff dimension escaping in the 2 classes in class B and class S. For class B function, it was a result of Becquerel and Coulters in 2012 that every number between 0 and 2 can be attained as a Hausdorff dimension of escaping sets for function in class B. So on the other hand, recently we saw that for class S function, you can also have a similar result. Of course, we prove this with a different method. We use query conform mappings to go to p function and also power map to control the growth of function. But roughly speaking, there's no big difference between class B and class S about this Hausdorff dimension or escaping set. So all values can be attained. But if we want to move a little further to see that how many singular values are really needed to attain each possible singular value. First, I recall you the result, which is a result by McMullen and also Glassky and Coders. You combine these two results, you see that Hausdorff dimension of the scheme set for function in S2 is either 2 or 1/2. Well, this is because if there are only 2 equivalence classes in S2, one of them is exponential map, then the scheme set 2 by McMullen's result. Another one is roughly tangent family, then the scheme set is 1/2, which was proved by Glassky and Coders. But in our result with R. Speinberg, with Magnus, we actually constructed function in S7, for which the escaping dimension can attain every number between 0 and 2. So, and also if you slightly modify the argument, possibly you can take this for some SQ for some Q bigger than 7, but I'm not claiming that this is for every Q bigger or equal than 7. This is because the restriction it's because the restriction of the method is does not give every value bigger or equal than 7. So then a natural question is between what happens between S2 and S7. So which is the main result I'm going to present today, which is we can show that in S4 the Hausdorff dimension, and we have a similar result as before for the class for S7. You can attain every number between 0 and 2. So more precisely, we can show this for given number though between 0 and infinity. We can construct the function S4 for which infinity is not a asymptotic value. Well, because otherwise we have 4 dimensions and the missing result by Weiwei Cui and Speiser. So and such the Hausdorff dimension is given as 2 row over 1 plus row. And clearly, if you change row, you can attain every number between 0 and 2, but not 0 and not 2. So the main point is then to construct function in S4. It's for which this result holds. So before I give some detail of construction, I want to outline the ideal proof. The main idea is actually you choose where starts p function, and you consider 1/4 of the p function. It has basically it is a sector. It has 2 boundaries, two banks. You glue the 2 banks together using query conform mappings. If you choose this p function carefully, then you can attain every possible value of growth, every possible growth, every orders between 0 and infinity. But this kind of thing, query conform mappings, will only give you query memorphic function in the plane. So then we need to use this is the following standard procedure. You use measurable Riemann mapping stream to get a meromorphic function and also query conform mapping of the plane such that G is F composed with psi. So, but we know everything about the query meromorphic function D. We don't know about function meromorphic function F. So we need to control the behavior of the query conform mapping psi. So this is ensured by the classical Teichmüller-Wittig Belinsky result. So in our case, it's quite simple because the query conformal surgery only happens in 2 half strips. So it has finite logarithm here, and this implies that the query conform mapping process is roughly identity map near infinity. but then estimate of this Hausdorff dimension of escaping is standard method, which the upper bound follows from the result of background encoders, and the lower bound you can use Macmillan's lower bound estimate of the Hausdorff dimension. So this gives the dimension estimate. So, any questions? Okay. So, so first I'll recall you the p function. Where starts p function? The p function is a doubly periodic function. You define for a non-real number tau. You define this lambda, which you can call it a lattice. And where starts p function defined by this formula, which is not important to us now. But it has some properties that the function is doubly periodic with periods 1 and tau. And it belongs to S4 with 4 critical values, which are at P of 1/2, P of tau over 2, P of 1 plus tau over 2, and also infinity. Infinity is a critical value, but this P function does not have any asymptotic values. Moreover, the function, the order growth of function is 2. You can estimate. So recall the number row we have given in the main result. Given this number row, we can choose alpha and tau, and such that the row can be represented in this formula. But roughly speaking, this alpha is the argument of the period, tau of the p function, and tau is another period. Yeah. So with this alpha and tau, we consider p function with periods 1 and tau, such as the argument of tau is alpha. So, and then what we're going to do is that we restrict the function to this sector, whose argument is between 0 and alpha, and we identify these two boundaries, so that we get so that we can map a slit plane or a plane slit along some curve to this sector, and then we compose by p function. We see whether the function will be a Riemann-Morphy function. So then we define this number eta, which also depends on alpha and tau, and then we consider a spiral function. Roughly means that it maps a spiral, the plane minus a spiral, to a sector. Yeah, this the map is to the power eta, where eta is a complex number. So with this number, with this spiral function, if you compose, if it is composed with the p function, you get a Riemann-Morphy function in the plane, which except for the spiral. You are not sure whether the function will extend continuously across the spiral. Yeah. So what we are going to do is that we have to change a little bit. First, to do this, instead of considering a sector, we have to consider the curved sector. Roughly means that you consider, first of all, recall for the p function, you have this conform mappings, yes, between this parallelogram mapped to unbounded domain on the sphere, which passes through the critical values, and this marked point are critical values. The corresponding points in left hand side is a critical point. So, and then you consider a curve passes through the critical points, which are at p of 1/2. P of 1/2, and you pull back this curve. Of course, this map, this curve has infinite many points. It's half of the curve has a pre-image in this parallelogram. So what we are going to do is choose these two curves, two periodic curves, along the boundaries of this sector. Yeah, we only consider this pre-image, which are roughly oscillating along the boundaries. And what you get is actually it's not sector, it's a domain which is bounded by two periodic curves. So what you get is such domain. And but we want to compose with the spiral function. But so for this purpose, we have to we have to define a map which is from the sector to this curved sector. So we call this a swing map. Basically, it's a quadratic form mapping. And what we are going to do is that we choose two curves, exactly two curves with the same arguments, and then we are going to do quadratic form surgery in this half strips, these two half strips, and for this purpose, we first cut these strips into two substrips, and both on the upper and also maybe I use something. Yeah. So what we are going to do is that we are going to do some surgery between here and here, here and here. So, and we leave the rest of part unchanged, and we hope that this will give a welcome to the map. Yeah. For this purpose, first, because you have a periodic domain, because this curve, because this curve, so this is the periodic curve. It's a periodic curve with a period is tall, and you can find a conform map which maps this part to this part. This is a conform map. But in practice, when we do this surgery, we have to consider construct this conform map between the bi-infinite half strips, bi-infinite strips, and also bi-infinite curved strips. But then we restrict the conform map to this part, and then we define a quadratic conform map between these two city regions. So between this and this, we use quadratic conform mapping. The map is like this. So we do quadratic conform interpolation. The boundary from here to here is this extension of this conform map. And from here to here, you have identity map. But the function, the extension of the conform map to the boundary is a periodic function, also a periodic function. And from here, the identity, you can define a quadratic conform mapping here. And also we do the same way here, from here and here, you have extension. From here and to here, you have identity map, and you do interpolation between these two domains. And in this way, you can get, you have, at least you define a quadratic conform mapping between these two half strips, and on the rest of the parts, you define as this identity map. You have identity. So in this way, you have defined a quadratic conform map between the sector minus this parallelogram to this curved sector minus this this domain, this bounded domain here in the left corner. And then the next step is that, but because with this quadratic conform surgery, if you compose with spiral function, and then if you compose with spiral function, you consider this P of phi of H, you still do not have, the map still cannot extend continuous across the spiral, because this is just a conform map. Because this from here just a conform map, it has no other properties between the for the extension. So we have to modify this map again in order to have an extension. So you have a correction map which defined between sectors and sectors. So roughly speaking, it's the same as before. You define a quadratic conform interpolation between, let me see, between here is identity map again. And between here and here, you have to do correction because if you have point here, you expect that this point here is corresponding by a spiral map to a point here. This point, a point on spiral, will map to 2 points along the 2 boundaries of this section and compose with a quadratic conform mapping. And then applied by P function, you hope that you can map them to a simple, then you have a continuous extension. But it is highly possible this is not happening. So we have to need this correction map. The correction map is basically defined between identity and this map from the boundary here to here. By first you go through here and to here by a P function and you go back to here. So in this way you have defined just the P function, quadratic conformal interpolation. But roughly you can also do this correction map on this side, but you only need to do this for once, and it will be enough to remove this discontinuity. Yeah. And yeah, this is. So we just define everything along this half strip except and the rest will be just identity map. Of course, we still leave something unchanged, which is this part, which is this part to this part, and this part, if I recall, it mapped to something like this, some curved domain, yes. But this we do this by using this quadratic compound extension to some bounded domain. Yeah. So with this construction, what we have in hand is a quadratic morphic function which is defined in this way. So first we have a spiral function which maps a plane minus spiral to some sector, and you do this correction and you do this stringing map, both are quadratic conform mapping, then you compose with the P function. And in this way, this function G will extend continuously across this spiral. So you get a quadratic map of function in the plane, but we notice that the dilatation of the supporting set of dilatation is only along the 2 half strips. It's not on the rest of the parts. So with this, then we can use this manifold dimension theorem to get a quadratic mapping psi and the meromorphic function f such that you have this relation. You really get a meromorphic function f, which is a function we want. But then we want to estimate the distribution property of this function. We apply this Teshmiller-Witte-Spelinsky result. So it says that if you have quadratic conform mapping the plane and hypothesize the dilatation, if this integral is finite, you know that the map is normalized to be an identity map at infinity. So with this result, in fact, because we know the information like the distribution of poles of the function capital D, then with this result, we can deduce some distribution properties of the poles of the meromorphic function f. Then the order of function f can be estimated by the counting function of the poles and the above mentioned result of Teshmiller. Then you can get the order of the function, and you know the distribution of the function, and you also know the multiplicity of function, the multiplicity of poles, which are always 2. So basically, then you can, because the function capital G has only 4 quadratic values, it has no asymptotic values. So the meromorphic function also has only quadratic values and no asymptotic values. It belongs to S4, and the multiplicity of the poles is 2, and you know local behavior of the function. If A is the pole, then the function roughly behaves like B over D minus A to the power 2, and A, the modulus of B is roughly this function, can be estimated in terms of modulus of poles. So then you can combine the result of Macmillan and background encoders to get to the upper bound. to get the very precise estimate of the Hausdorff dimension of this escaping set. Of course, because rho is taken between 0 and infinity, not 0 and infinity. So the dimension is only between 0 and infinity. But if you want to get function or if you want to get a function S4 with 0 Hausdorff dimension, then there are many functions with this property. There are functions given by Lanny, by Ermanco, maybe even earlier by Teixeira. But roughly, you can just consider, you can do a function of dimension of its spin is 0. You can consider the function roughly behave like a P function composed with inverse branch or hyperbolic quotient. And the order function is 0 and has bounded multiplicity. The function belongs to S4. It has 4 single values. They can apply directly without a background coders to get the dimension 0. So if you want a 4-dimensional escaping set, it's 2. Sorry, it's 2, and then you can consider the function like P of like 2 pi hyperbolic cosine of that. Yeah, and this function has infinite order, but as you can expect, if the order goes to the infinity, then the dimension should approach number 2. So the dimension also approaches 2. Across the multiplicity is supposed to be bounded. So for this function, order grows to infinity and multiplicity is supposed to be bounded. And you can estimate with the like Marlin's result, which gives a lower bound of the estimated dimension to get that the function has 4 dimensions. So I think I have just proved that every number between 0 and 2 can be obtained as the Hausdorff dimension of the escape set in the class S4. Maybe I'm a bit ahead of time, but thank you very much. Thanks for your attention.
Are there any questions or comments? Yeah.
Can I ask a question? Or is
Yes.
someone else? So you construct functions with 4 singular values. The obvious question is, can you construct functions with 3 singular values?
Yeah, I think this is true. And this is an ongoing project with water, but it's not finished yet. But I have to say that with this method, it's not possible. It is not possible that you can reduce the number of single values, because essentially a number of single values in our example is the number of single values of P function. Of course, you can have elliptic function with 3 single values, but the period of these functions are quite rigid.
Yeah.
So the modules must be the same, but here the order growth or the constructed function also depends not only on argument, but also on the modulus. So this number row. So with this method, it's not possible. But we have to use another method. This is don't work with water.
Okay, thank you.
Or comments?
Hi, Weiwei, thank you for the talk. I was going to ask the same thing as Lasse, so I will change my question a bit. What about the other values, 5, 6, and also you said that you didn't know for Q greater than 7, right? I understand it's because of the method, but why, if Q is larger, what are the obstructions there?
You mean, let me see, is here? Like,
yeah. Can you find, I mean, why, for which values of Q do you think you can
for
get the
some
same?
values, for example, if if you, I think this value you can take like 3 n plus 1. N is any integer with bigger or equal than 2. 3 n plus 1 because for this result we use 2p functions. And the number of singular values is the number of the sum of this number of singular values of these 2p functions, which is 4 plus 4 is 7, because the infinity is all left. And but of course you can use many p functions. For example, in our example, we in upper half plane we consider 1p function. In our lower half plane we consider 2p function. But this construction it's quite flexible, because you only need a 2p function has one period which coincide. On the another period is quite flexible, so then you can divide the upper plane into maybe sectors. In each sector you consider a p function. Then you can increase the number of single values. But again, because we are using p functions, and the number q has to be quite restricted, either like 3n plus 1, or maybe you can change to 3n. If you're lucky, some p functions will have same critical values, then you just reduce 1. But I don't know if it can change every q bigger or equal than 7.
I see. Thank you.
Yeah.
Any other questions?
Oh, sorry. I think Walter wants to say something.
Okay. Well, couldn't you just replace a p function by some, so given any q, so couldn't you just sort of, instead of working with a p function, first sort of construct some elliptic function which has, say, precisely q singular values, and then maybe try to do something similar what you did with the p function with that particular elliptic function? So that you, that you replace a p function by another elliptic function.
But with q singular values, yes.
With q singular values, yes.
Okay.
So I was going to say something similar, but why can't you just move one of the critical values slightly off? I mean, you've got all of the critical points mapping to these critical values. Yeah. Couldn't you just move one of those critical values slightly off, and you create an extra critical value? And you shouldn't change anything really of the behavior of the function near infinity. So can't you just increase your number of critical values that way?
Good idea. Thanks. Yeah.
Okay. Any more comments? No? Okay, if not, let's thank Weiwei again for a great talk.
Thank you.